In this section of 13.1, we're going to be trying our hand at sketching level curves. Our function f of xy equals x squared plus 2y squared. This represents a surface in space, a 3D surface. But as you know from experience, those 3D surfaces can be kind of tricky to graph. So the idea here is to sketch a two-dimensional contour map, or sketching those level curves. In this case, where a function is given here, and our c levels, c equals 0, 2, 4, 6, and 8. We're going to look at the first c level, and we're going to set the function equal to that c level to get x squared plus 2y squared is equal to 0. Well, in this case, the only way that x squared plus y squared, you can add those together to equal to 0, the only way that that can happen is at the point 0, 0. So if we sketch a point on the graph here at 0, 0, when the surface is sliced at the height of c equals 0, it only touches the surface at a single point. Let's look at the next c level at c equals 2. This was c equals 0. Let's look at c equals 2. You're going to set the function x squared plus 2y squared to equal 2. Hopefully you recognize this as a graph of an ellipse. If we divide by 2 on both sides of the equation and rewrite it, we get the equation x squared over 2 plus y squared over 1 is equal to 1. This is a graph of an ellipse where you would go square root of 2 units to the right, which is about 1.4, and the square root of 2 units to the left, which is about negative 1.4. You're going to go up 1 on the y-axis and down 1 on the y-axis. And that contour line, when the c is 2, is the graph of this ellipse. Okay. Now let's look at the contour line when c is equal to 4. We have the equation x squared plus 2y squared is equal to 4. Again, this is going to be an ellipse. We're going to divide by 4, and the resulting equation is x squared over 4 plus y squared over 2 is equal to 1. This is an ellipse where you are going to go 2 units to the right and square root of 2 units up. So that's up 1.4, about down 1.4, and connect those points with an ellipse. So as the elevation increases, the ellipses are getting larger. You can do the same thing for c equals 6 and c equals 8. For c equals 6, you're going to set the function equal to 6 and simplify and graph the result. So when you simplify this, you get the equation of the ellipse x squared over 6 plus y squared over 3 equals 1. Now do the same thing for that last c level, c equals 8. Set the function equal to 8 and simplify the result. When you sketch that last one at c equals 8, you see that those ellipses end up being pretty close together the higher the sea level. So the surface is very steep as the elevation increases. Let's try our hand at this function of two variables. F of xy equals the natural log of x minus y, where the c is equal to -2, -1, 0, 1, and 2. I'm going to show you a little shortcut for this one using a calculator and solving it in such a way where each time you're changing the value of c. So what you can do first is to set the function natural log of x minus y equal to c to begin with. Now we would like to use a graphing calculator In order to graph, you need to solve this for y. And we'll plug in the c levels later after we solve this for y. And what you can do here, since this is a natural log, you can take e and raise it to both sides. And e to the natural log of x minus y can be simplified to x minus y equals, oops, x minus y equals e to the c. Now we can rearrange this. We can say negative y is equal to negative x plus e to the c. I wanted to get y by itself. And then by changing the signs here, I get the equation y equals x minus e to the c. Now we can plug in the c's for each of those and graph the corresponding level curves. So let's look at setting up a table when c is equal to negative 2. Y is equal to x minus e to the negative 2 power. We'll use a graphing calculator to sketch these all together. When c is equal to negative 1, y is equal to x minus e to the negative 1 power. When c is equal to 0, y is equal to x minus e to the 0 power. When c is equal to 1, y is equal to x minus e to the first power. And when c is equal to 2, we have y equals x minus e to the second power. Let's use a graphing calculator and sketch each of these level curves. And this set of level curves starts at a c level of negative 2. So in other words, when the z is equal to negative 2 on the graph of the surface, this is what the x and the y will equal. Now in function mode on your calculator, go to mode and make sure you're in function mode. Press the y equals, and we're going to enter each of these equations. X minus e to the negative 2 power and you can start off by doing a standard zoom. Going to zoom and going to a standard zoom. So the first level curve when c is equal to negative 2 is a line. Let's go ahead and enter the rest of the y equals into the spaces provided. So I've entered the 5 equations into the y equals and I'm about to press graph. When you're looking at the graph, keep in mind of the elevation. The first graph is at the lowest elevation, the second is slightly higher, the third, and so on. As the lines are graphed, pay attention so you can kind of get an idea of what the 3D surface looks like. So in the first elevation, the second elevation, very close together. You can see they're getting a little bit further apart. So at the low elevations, very, very steep, and as its elevation increases, those lines are spaced further apart, so you get something that is not as steep. Do you have an idea of what this graph looks like in space, a 3D surface? Well, it looks like kind of like a piece of paper that's been folded or rolled over. In the previous examples, we sketched level curves which corresponded to surfaces in space. That's when you have a function of 2 variables, you get a 3D graph. However, when you have a function of 3 variables, it's a 4-dimensional concept here. So instead of graphing level curves, you graph level surfaces. If f is a function of 3 variables and c is constant, the graph of the equation is a level surface of the figure shown here. Level surfaces here. Well, an example of a function of 3 variables could be, say, temperature distribution. The location in space is 3-dimensional. The temperature at each location gives you that 4th dimension. So one way to represent that is by using color. With computers, engineers and scientists have developed ways other ways to view functions of three variables. This shows a computer simulation that uses color to represent the temperature distribution of fluid inside a pipe fitting. Looks like the cold water and the hot water, and as they're opened together, you can see the distribution of the temperature. You can also use computer graphics. It shows a computer-generated graph of the surface using 26 traces taken parallel to the YZ plane. To heighten the three-dimensional effect, the program uses a hidden line routine. So this is something, if you were to plug this into a graphing calculator or 3D graphing software, you could get one of these images. You get the illusion of the 3D image, although it's a flat surface, your flat computer screen. You see the dimension. Here are some additional ways. Now the graphs can look very different depending on how you're viewing them from. These are the top three graphs are the same surface, but looking at them in different views. You can see the X and the Y axis rotated a little bit here. These on the bottom are the traces. We call these single traces and double traces and level curves, all of the same function of two variables. Here we have a few more examples. We have a function here. You can see kind of a wavy egg crate pattern here for the function of xy equals sine x sine y. Here we have another surface, another surface. Try experimenting with some of the online computer graphing software that's available and graph some of these surfaces. A lot of times you'll be able to rotate these graphs and really get a look at these images from many different viewpoints.